So we're going to talk about chain rule, and chain rule is really the third major concept in differentiation. You've talked about product rule, you've talked about quotient rule. Now we need to talk about chain rule, and chain rules are when you have nested functions, when you have a function inside another function. And this as if y equals f of u is differentiable. So if this outside function is differentiable, function of u, and u, the inside part, is g of x, which is another differentiable function. So if the function g of x is inside the function, then f of g of x is differentiable function, and dy dx equals dy du over du dx. It can also be written as this. Okay, this is kind of the one that I like, because what it says is find the derivative of the outside part and then times the derivative of the inside part. And that's kind of what we're going to do with this whole thing. So let's do an example. Let's find the derivative of 3x minus 1 cubed. All right, so I want to find the derivative of this. I kind of need to identify the two functions. Well, the first function is this cubed that's hanging out outside. That's the outside function. The inside function is this 3x minus 1. So when I want to find the derivative, I take the derivative of the outside function. So just pretend like this whole inside part is x. So the derivative of the inside function is 3, don't change what's inside, squared. So I brought the 3 down and I took 1 away. So I brought the n down and I subtracted 1. Times, I take the derivative of the inside. Well, the derivative of 3x is 3, derivative of a constant, of course. So I've taken the derivative of the outside function, the derivative of the inside function, and I can make this look a little better. 9, 3x minus 1 squared. That's essentially what chain rule is. Now there's a bunch of strange cases that pop up. In the rest of this video, I'm going to kind of discuss those. They like to do this. Any of your inverse functions where you're in the denominator, the easiest way to deal with these is to go ahead and rewrite this as x squared plus x to the negative first. That's what the inverse function means. Then you can kind of see where this chain rule is coming in. This negative first is the obvious outside, and the x squared plus x is the inside. So to find the derivative, I find the derivative of the outside function, which is this negative 1 power. So I bring the negative 1 down, don't touch the inside, and subtract 1 from the power, times the derivative of the inside. All right, so the derivative of x squared is 2x. The derivative of x is 1. Now I just need to simplify. So I've got negative 1, so I could probably put it as negative 2x plus 1. And the negative power means that I'm going to take and put it down in the denominator. All right. Let's talk a little bit about what happens when we get into a little trig here. So what's my outside function? What's my inside function? I need to recognize that, yes, I do have an inside function here that's a little linear function. And I do have the outside function, which is cosine. So when I find the derivative of cosine is negative sine, don't change the inside, times, take the derivative of the inside, well, 2 pi x. Don't make the mistake that pi is a variable. Remember, pi is just a number. It's a constant. So the derivative of 2 pi x, the constant rule says the 2 pi just stays there, and derivative of x is 1. So the derivative ends up being 2 pi. So my derivative is negative 2 pi sine of 2 pi x. Another situation that we come across, f of x equals the cube root of x squared minus x plus 1 to this squared. When I'm doing ones like this, there's a couple ways that you can do this. You could actually do the chain rule twice. You could find the derivative of the outside function, the cube root, then the derivative of the inside function, the square root, then the derivative of that. For me, when I'm doing these, it's easiest to remember my properties of exponents and just recognize that I could write this as x squared minus x plus 1, second power, third root. So to the 2/3 power. Then when I find the derivative, I find the derivative of the outside. 2/3 minus 1 is negative 1/3. So I found the derivative of the power, and then I multiply that by the derivative of the inside. 2x minus 1, and the 1, of course. So I rewrite it. I'm going to put this up top to 2x minus 1, 3, and then x squared minus x plus 1 to the 1/3 power. And no, you don't have to rationalize the denominator. Okay, we'll get a little more complex because now we have an obvious situation where we have a product rule and a chain rule involved. All right, because I have this x squared, and then I have this, also have this 2 minus x squared, square root of that. So I would rewrite this first as x squared times 2 minus x squared to the 1/2 power. And then I'm going to use chain or product rule. So the first times the derivative of the second, 1/2. This is chain rule. And then you don't forget, you got to take the derivative of the inside. So there's the first times the derivative of the second plus the second times the derivative of the first. Oh, there's some nice cleanup that can be done here. This isn't going to get real clean, I don't think, but if I wanted to, I could factor out a 2x since they both have a 2x in common. That leaves me with a negative right there, an x squared, 2, a 2 minus x squared to the 1/2. So let's see, make sure I took care of everything. I took care of the negative, I took care of the x squared, the 1/2, there's the 2 for that. Yeah, that's all good. Plus 2 minus x squared to the 1/2. And I factored out that 2x. Did I have to factor out that 2x? No, that would have been the same thing. That just makes it a little prettier. I would not try and combine those. It's not hard to do, but it's pointless. All right. So since we just did one with product rule, we'll obviously do one with quotient rule. Once again, I'm going to rewrite this the same way. It's to the 1/3 power. And then I'll do quotient rule. Low D high minus high D low. Okay. So 1/3 x squared plus 2x to the negative 2/3, which is 1/3 minus 1, times the derivative of the inside, 2x plus 2. Wow, that's not very good. So the derivative of the inside is 2x plus 2 all over low squared, which would put that at the 2/3. Okay, so this is not looking super pretty. Oh, yeah, no, that's correct. Okay. I forgot to square it here. I was looking at it. It didn't look right. There's not a great cleanup to this. Not that it's obvious. I mean, I could factor an X out. That doesn't matter, though. Not really. So if I was going to write this as my final answer, I would probably, you don't ever really want to leave negative exponents. So I would say 2x x squared plus 2x to the 1/3 minus, what do we have? An x squared, a 2x plus 2, a 3, x squared plus 2x to the 2/3 all over x squared plus 2x to the 2/3. Now, could I simplify that, combine these two, and then multiply by the, yes, you could. It's just a lot more places to make an error for an unnecessary reason. I would go ahead and leave that as my final answer. All right. So cosine 3x squared. We kind of did one like this. Not exactly sure why I threw this one in there as well. The derivative of cosine is negative sine. Don't change the inside. Times the derivative of the inside. Done. This is more what I was thinking. These are kind of difficult because you have to recognize what this sine cubed means. Remember, this is the same thing as saying sine of 4x squared cubed. So this is one of those cases where we're going to end up doing chain rule twice. So I do the derivative of the outside times the derivative. So I did the derivative of the cube. Now I got to do the derivative of sine 4x squared. Well, the derivative of sine is cosine. Don't change the inside. And then I have to do the derivative of the inside. 4x squared's derivative is 8x. So I did the derivative of the cube, the derivative of the sine, the derivative of the 4x squared. You just keep working your way in like those nesting dolls. So 24x sine of 4x squared cosine 4x squared. All right, so that's the basics of chain rule. Now, this is also the section where we bring back natural logs and really start talking about natural logs. Remember, your natural log is basically your log base E of x. So remember, natural logs is when your base was E. Sorry, it was lights. So the derivative of the natural log is 1 over x. The derivative of any constant raised to the x power is the natural log of that constant times a to the x. This is kind of like, if you remember, this is when we talked about the derivative of e to the x, we said that the derivative of e to the x is e to the x. Well, if I take it in this perspective and I replace a with e, then the derivative of e to the x would be equal to the natural log of e times e to the x. Well, going back to our log rules, if the base and this number match, this is just equal to 1. So that's why the derivative of e to the x is e to the x. But the derivative of, say, 2 to the x would be ln 2 to the x. All right, and that's just kind of explained a little bit further here. This one is just saying, well, what if we replaced x with another function? So what if we had like 2 to the 4x squared? And I wanted to find the derivative of that. Well, it just says it's the natural log of the base times what we had, 4x squared, 2 to the 4x squared, times the derivative of the upper function. So it would be times 8x. And we could simplify that a little bit. So if we're given one like this, the natural log of x squared plus 1, to find the derivative, well, the outside function's a natural log, and the derivative of a natural log is 1 over x. So the derivative of the natural log of that would be 1 over that. Then we have to find the derivative of the inside, chain rule. So derivative of inside's 2x. So my derivative would be 2x over x squared plus 1. All right, I just made this one a little bit more fun, threw in one extra little piece, but it's no different. The derivative of the natural log is 1 over whatever you're taking the natural log of, times the derivative of the inside. Well, you just have to recognize that the squared function is one function, and then inside is the 2x plus 1, so you have to multiply by another 2. So I took the derivative of the log, then I took the derivative of the squared, then I took the derivative of what was left. That would clean up 4 times 2x plus 1 all over 2x plus 1 squared. You could cancel out one of the 2x plus 1. All right, so find the derivative of 7 to the 2x. So if I want to find dx of 7 2x, then I go back to my rules that said that if I have this situation, it's just the natural log of the base times AU times the derivative of the exponent. So 2 ln 7 to the 2x. Not real pretty. All right, these are the ones that you do see on the AP test because they like to see, hey, do you know all the things? Remember what we just said a little bit ago on that first slide, that ln is the same thing as log base e. And one of our properties of logarithms said that if we have an exponent, that we can actually bring that out front. That if we have an exponent, we can bring that out front. That was one of our properties of logarithms. And then ln e is equal to 1. So it's, sorry, 2x times 1. And then the derivative of that is simply 2. So here are all the differentiable rules that we have so far that you need to know. All right, these are available in the book. It's also, you know, if you want to pause it or whatever, any that you don't know. But these are all the rules that we have so far. So go ahead, pause the video, see if you can do this one here. Okay, now that you've had enough time to do that. So if I want to find the derivative of cosine 4x to the 5th. All right, I can do that. Got to take the derivative of the outside function. I'm going to work my way in. Times the derivative of the inside function. Times the derivative of the innermost function. With a negative out front. All right, pause the video, give this one a shot. Now that you have time to do that, recognize that this is the product rule. So the first times the derivative of the second. Okay, so we have e to the negative 5x. And if we're taking the derivative of e to the negative 5x, we have to remember that this is the same thing as e to the 5x negative 5x times du, the derivative of the inside, negative 5. Because the derivative of e to the x is e to the x, then you have that second function because of chain rule. So the first times the derivative of the second times the derivative of the first. I mean, this could clean up a little if you were so determined, into x squared e to the negative 5x times negative 5x plus 3, right? Taking x squared out, taking e to the negative 5x, yeah. Do you have to do this step? No, it just makes it nice. All right, last one, see if you can do this one. All right, so find the slope of the tangent line to the function through the point. Not really even a chain rule problem. This is just a straight quotient rule problem. So quotient rule, I'm going to go ahead and put the negative with the 2x squared, just so I don't forget where it goes. So I'm going to do low d high minus high d low all over low squared. I'll do just the basics. Negative 4x cubed minus 4x minus the minus is a plus 4x cubed all over x squared plus 1 squared. Those are going to cancel each other out, so I end up with negative 4x over x squared plus 1 squared. It says find the slope of the tangent line. Okay, so here's my slope right here. So if I evaluate this at 1, I end up with negative 4 over 1 plus 1 is 2, 2 squared is 4. So I end up with a slope of negative 1. So y equals negative 1x plus b. Need to find b. So I can plug in 1. I know it goes through this point, so plug in negative 1 there. And I get b equals 0. So the slope to the tangent line, the slope of the tangent line to this function through this point is y equals negative x. And you could use your graphing utility to check on that.